Perfect. Thank you so much, MK, for the introduction. As MK mentioned, I work for ASAP. We build NLP solutions for enterprise companies. You can learn more about us in the expo because ASAP is a proud sponsor of Connect Forward this year. So feel free to go to the expo and chat with some folks from ASAP there as well. One of the domains that ASAP concentrates on is customer care. So if you think about it, a big portion of customer care is chat. MK mentioned that I managed the chat team at ASAP previously. So if you think about it, customer care ultimately is an end customer coming to you over either a digital chat or voice chat, and then talking to an agent to find some resolution for the issues that they're facing. I wanted to share some interesting problems we encountered while running our chat services in Kubernetes and what lessons we learned from it. Think about it as an application developer's perspective about how we shielded, about whether we are really shielded from knowing the details about Kubernetes as application developers. What I intend to cover today is just a high-level overview of Kubernetes, introducing the concepts that are going to be important for us to understand the three problems that we will then dive into, that we faced and learned from. And then finally, just some takeaways and things to bear in mind. So what is Kubernetes? This definition is taken from the official Kubernetes docs. It says Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services that facilitate both declarative configuration and automation. So you can think about Kubernetes as a container orchestration tool, but it wouldn't be doing it justice. As an application developer, it takes care of a lot of stuff for me. It could take care of load balancing, it takes care of service discovery, it offers me secrets management, as well as configuration management. So it does a lot. And this is what I'm presenting is an extremely simplified view of it. The other thing that is very important from the definition is that it manages many types of workloads. You could run jobs, you could run stateless services, you could run stateful services with some caveats. But it is capable, it is really agnostic to what you really want to run on it. So looking at, again, a simplified view of Kubernetes, on the left-hand side, you have a control plane. You can think of control plane as all the components that manage your cluster. It governs the cluster, so to speak. I have highlighted only a few important ones, important in the sense for relevant to this talk. We have the Kubernetes API server in the center. Then we have the scheduler. We will go into the detail of how the scheduler works because it's relevant further down. And then we have etcd, which is a data store. If you think about it, Kubernetes is a massive distributed system, which means we need to store state somewhere. And that's etcd. The etcd is just a data store. The top right box shows us a node. It has a kubelet, which is a process that communicates with the Kubernetes API server. And then there are pods that run your applications. The bottom right box shows the pod broken down even more. This is to illustrate that a pod could potentially contain more than one container. So you can see a database container and an app backend container in here. The two things to bear in mind is that even though a pod can be made up of multiple containers, for Kubernetes, pod is the smallest unit. It cares about pods. And that leads to some challenges, which we'll talk about. But the best part, in my opinion, even though the definition does talk about automation, which kind of implies imperative, there is the declarative component of Kubernetes, which in my opinion is the best part. You can wish for something to happen and specify it in YAML, and then K8s magically just makes it happen for you. I say that with a small asterisk because the talk is ultimately about how this is not magic. So digging into it a little bit further, how does this actually play out? How does the scheduling and the scheduler work? So this is a very simplified sequence diagram of how scheduling works. Scheduler is the component that matches a node in your cluster with a pod which runs your application. So scheduler is the one that is going to decide where in the cluster your application runs. It does this in two steps: filtering and scoring. So whenever a command is issued to the API server to create a pod, for example, here we are using a command line tool called kubectl to ask for a pod creation in step one. The scheduler is talking to the API server to find out if there are any unassigned pods, as you can see in step two. When it finds that there is a pod that needs an assignment, it will run some algorithms and figure out what is the best node to run that pod on. So in step three, you can see that it's deduced that, let's say, for example, pod A fits best on node A. And it will assign that to node A and communicate back to the API server. Now the kubelet on the node A is watching for any pods that might have been assigned to node A. So that's happening in step four. It finds out from the API server that yes, the scheduler decided that the pod A should run on node A. So please do something about that. So kubelet in turn then talks to the container runtime, which in this case is Docker, and creates the pod on node A. Depending on whether the creation of the pod was successful or not, it will report back a status to the API server. And so when I use my command line tool, kubectl, to again find out if my pod creation was successful, I will know the result. Having gone into the brief overview of Kubernetes, now let's jump into the first lesson. The first lesson is about the scheduler can only be so smart. The problem that we saw was we had intermittent chat latency spikes in production. With the support of our amazing SRE team, we did what all good engineers do, which is we went looking into our metrics to find any correlations. What we saw was a high IO8 spike at the same time as the chat latency spikes on the nodes where the chat servers were running. You can see it in the graph. So you can see that you have a chat latency spike of over 20 seconds, which is not great. And then you have an IO8 of about 25, 30%. IO8 is a slightly tricky metric to understand. So let's break it down. Let's think of it as you have one CPU, and then you have a process that does a synchronous disk write. Let's say that disk write takes 30 milliseconds to do. So over 1,000 milliseconds, I'll be able to do 33 transactions, which means the CPU will be busy for 1/3 of the time, and the IO8 will be 66% of the time. Having understood that, let's see what was causing the IO8 spike here. We inspected the other services that were running on the node and found that some of our machine learning services were running on the same node as our chat services. These machine learning services were reading really big models to the size of some gigabytes into the at service startup. So when the container started, this led to high IO8, which you can think of kind of an idle CPU time, which means the chat request took longer to complete, and that caused the chat latency spikes that we saw. So what was the solution? And what did we learn? Well, first of all, we learned that yes, the scheduler will try its best to find the best node for you to run your services on based on the information that you give declaratively to it at the time you define your services. However, every service will have some interesting patterns at runtime. For example, in case of the machine learning services, we were loading up big models at container start time. So as developers, we know best how our services run. We also can observe how our services run and then make more intelligent decisions about how to run them. So in this case, what we decided was the best option for us was to separate out the chat services and the machine learning services and run them on different node pools. So a node pool is a group of nodes within a cluster that has the same configuration. So we created machine learning node pool, and then we created a chat services node pool. And the best bit is that you can do it declaratively. So you create the node pool, and then in your pod definition, so let's say in a machine learning service pod definition, you specify affinity, especially node affinity, which is required during scheduling. So it's a helpful hint for the scheduler. And we are saying that please choose a node for this pod where the node matches the instance group in nodes ML, which means please give me a node from the node ML node pool. What this meant was we would never then run machine learning services and chat services on the same nodes, and therefore we don't give them a chance to clobber each other and can maintain our chat SLA. Great, so now that we learned about scheduling, let's try to figure out what Kubernetes does when it has to purge or kill or evict pods. Is Kubernetes smart enough when it comes to that, or is it just random? Let's dive into the second problem that we noticed. At some point, as happens in every life cycle of a chat system, we were required to scale. We wrote a load test, we made a lot of performance improvements, and we were running load tests to constantly evaluate if our enhancements were working. But at some point, we plateaued. We couldn't figure out why our load tests were not repeatable. Horizontal scaling wasn't working. We were seeing random errors everywhere. Performance was bad, even though chat services were within resource limits, and we saw some saturated nodes. Now, what does saturated nodes means? So this is obviously not a production snap because we learn from our mistake and hopefully we don't saturate any nodes in production. But I'm running a Minikube on my local and I simulated overcommitment here. So let's dig into this a little bit. You can see that there are 4 demo apps that are running, and I have asked for half a CPU for each of them, which means the CPU commitment is already at 2 CPUs, which is the only CPU available for my Minikube cluster. As you can see here, this means that the limit commitment is already at 100%, and the memory commitment is actually at 109. You have to understand that the pods are still running because my request commitment is not yet reaching the limits. But what this means is there is flex, and if any of my demo apps decide to take the advantage of that flex, they can put us over the 100% or over 109%. And that means Kubernetes will have to make decisions about pods to sacrifice. It's not in our best interest for this to be random. So going back to what issues we were seeing was random errors. So, which is why I specify that it is not in our best interest for it to be random. So we need to figure out how to make this make this a little bit more logical. So a short detour to be able to understand how Kubernetes actually makes decisions about something like this. On the right hand side, on the left hand side, you can see there is a pod definition or a part of the pod definition, which is related to resources. How much resources does your service need to run, or it thinks it needs to run? So for example, under resources, you have requests, and that is generally what a service owner is telling Kubernetes through declarative specification, that it needs 500 megabytes of memory and half a CPU to run its service. The other promise that the service is making is that it's not going to exceed 1 gigabytes of memory and not going to exceed 1 whole CPU. And that's specified in the limits. So this is usually the information that we can give the scheduler, and it can use it to request is usually what the scheduler will use to give you the right node to run your pod on. Now let's look at what will happen if we don't specify this in an informed fashion. So I'm going to play a demo video for this. Hopefully everyone can still see it. You can see that I have 3 demo apps running. I'm just going to pause here and talk about the fact that there are 2 containers in this demo app. So you will see it during the demo that in the pod definition, I have 2 containers. One is the database container, which is Postgres is what I've used. And the second one is just a chatter app. So it sleeps for a while, writes hello world, and that's it. So which is why there are 2 containers in the demo pod. Now we can edit the deployment. And another thing to note is that my Minikube setup, my cluster, has about 4 gigabytes available to it, and it has 2 CPUs. So what I'm going to do here is ask for 1.5 gigabytes of memory to run my application to begin with. I'll pause here again and talk about the magic that we said, which is K8s will do a lot of things for you. Let's say in production, I want to always run 3 instances of the demo app. K8s has some higher level, Kubernetes has some higher level constructs, higher meaning above the pod, so deployment, etc., where you can specify the number of instances of your services that you want to run. And Kubernetes will make the best attempt to always maintain those many instances of your services. So here I have used a deployment and I've asked for 3 instances of my demo app. I'm specifying that my database container within the pod requires 1.5 gigabytes each. So let's see what happens. I'm just watching the pods as they spin up. As I mentioned, I have about 4 gigabytes allocated to my Minikube cluster. And that means that I can successfully schedule 2 of my pods. 1.5 plus 1.5, 3 gigs within limits, great, it's working. So 2 of my pods are in the running state, but one is just pending. It's not being able to do much. Kubernetes is trying to give you the 3rd pod, but it's not working. So we will see what happens. Let's inspect this pod and see what's happening. So if we describe the pod, there we go. It's going to tell you exactly what went wrong and why the pod could not get into the ready state. You can see that there is only 1 node, 0 nodes available because you have done the commit, given the commitment already for the memory available. And now you don't have enough memory. There's just 1 gig available. You're asking for 1.5. So it's not going to work. Now, again, you have 2 healthy pods running and 1 non-healthy pod. Okay. When I installed Minikube, one of the things I did was I enabled the metrics server plugin. What I wanted to demonstrate is that we need to know the usage of our service to be able to make intelligent discussions and help Kubernetes along to make intelligent decisions about scheduling our services. So here, using the metrics server, I'm actually querying to find out what is the memory that my app is using. So I took one of the healthy pods that's running, and you can just query the metric server using that URL and print it out using JQ in a good JSONified format. And you will see that it's about 28 megabytes. Great. So here's what we are going to do next. We are going to breach the limit. We know that our real usage is 28 megabytes, but let's say that we breach the limits. Let's put the limit at 20 megabytes, which means your pod cannot really run because its normal usage is 28 megabytes. But I'm putting my request at 10 megabytes. What this means is that I'm going to be able to schedule the pod, but as soon as the pod starts up, it's going to breach its limit and it's going to get OM killed. You can see it's out of memory and Kubernetes had to kill it because it breached the promise of sticking within the limits. Now, why is this constantly going into a running state, a crash loop back off, and back into OM kill? This is again about the promise Kubernetes makes to you about trying its best to maintain the number of replicas you're asking Kubernetes to maintain. So you wanted 3, and it's trying over and over again to give you 3. However, they're just getting OOM killed. So that's for the demo. And that was a short detour to really understand how Kubernetes actually makes decisions about scheduling or killing, for that matter, purging the pods. So with that, let's talk about the suboptimal chat performance that we were seeing and random errors. You can imagine that the random errors were obviously because random pods were getting evicted as the node was reaching saturation. So what we saw was in our services definitions, and this doesn't have to be just the chat services. It can be any services that are sharing the node with your chat services. Some pods were not configured to have well thought through requests and limits for CPU and memory. Some just didn't have any configured, and some had very low ratio of request to limits, which means if it flexed and put the node over to saturation, it's going to adversely affect the rest of the services that are running on that node. So what did we do? We decided that we are going to give helpful hints to Kubernetes as to which pods are okay to sacrifice. And that can be done by assigning priority to your pods. How do you assign priority to your pods? You use what is called QoS, or quality of service configuration. There are 3 distinct types of QoS. One is guaranteed. It's the highest priority. Obviously, as the name indicates, it's guaranteed, right? Another is burstable, and then there is best effort. Guaranteed means that every container in the pod must specify a memory and a CPU limit. You can choose not to specify the request. However, if you don't, then K8s will automatically set the request to be the same as the limit. If you do specify the request, you have to make sure that it is same as the limit for the memory and CPU. This means that your pod, this configuration tells Kubernetes that this is the highest priority pod, and it will not be killed until the memory limit is reached and the pod is unhealthy. One thing to note about QoS is that it generally works off of the memory, because if you breach memory, you can get evicted, you can get killed, the pod can get killed. When you breach CPU, it just means you get throttled. Your service might slow down, or you might see some other side effects, but you're not going to get evicted. With burstable, you can think of it as medium priority. At least one of the containers in the pod has a memory or a CPU request specified. It might get killed when it exceeds the request and the node runs out of resources. So it doesn't have to wait for the limit to be breached. It could happen when your requests are when you're above your requests and the node is running out of resources. And finally, there is best effort. Best effort is the lowest priority. None of the containers have any CPU or memory requests or limits specified, and they're the first to go when the node is running out of resources. One thing to note here is that, as I mentioned before, the smallest unit for Kubernetes is a pod. But what matters is that if your pod is made up of multiple containers, you need to configure the request limits and memory limits for all of the containers within the pod for it to qualify as guaranteed. If you miss for any of them, then in that case, it immediately gets qualified as a burstable pod, and hence can get evicted if it breaches the request. So what we did was we audited all our services. We figured out the right configuration to apply, right QoS configuration to apply to it. And that kind of made us aware of the logic that Kubernetes might use in order to kill the pods. And that led to some predictability about what was going on in the system. And we weren't seeing any random errors anymore. Now, a question to ask here is, why can't I always use guaranteed? Sounds great. It's the highest priority. I'm just going to give all my applications the highest priority, and that's perfect. It's really a question of balance. If we ask for too much for each of the services and then the services are not using all of it, you're wasting resources, you're accruing cost for no reason. Sometimes you just don't need it. For example, maybe some of your services don't have any usage pattern for at night. So it's zero, and then why assign 1 GB to it? So as always, it's a question of balance, and you have to aim to be more right than wrong, which is why looking at your usage patterns in production and then making informed decisions is much better. Moving on to the third lesson that we learned is that we alluded briefly to multiple containers running in a pod. And we said that we saw that in the demo where the pod had a database container and an application container. And we said that if we want a guaranteed pod, then all the containers need to specify limits for CPU and memory. This already tells us that there is more to think and know about when we run multiple containers in a pod. What were the issues that we were seeing? So we were seeing some unexpected startup and shutdown problems. What were our symptoms at shutdown? Suddenly we heard about chats not working for some people, and multiple connection refused errors were seen in the logs. And then symptoms, on another occasion, we had issues at startup and SDKs wouldn't load. Chat services were failing to start up as well. So as all good engineers do, we went and looked into our metrics. We went and looked into our logs, found nothing other than the connection refused error, but nothing else that was indicative of a problem with the services themselves. So our minds went to the service mesh. So we run a service mesh. What is a service mesh? It reduces the burden on the application code by offloading the logic of inter-service communication and abstracts it into an infrastructure layer. If you think about the microservices world, everyone talks about how your service should have one responsibility, it should do it well, and that's it. So think about all the other things it needs to do, a service needs to do. It needs to have retry logics, rate limiting, etc. You can put all of those, yes, into libraries, or you can choose to offload it to a service mesh. In a container world, you want a container to do one thing and then do it well and offload all other concerns to someone else, for example, mutual TLS. So you have a service mesh, and a popular architecture for that is a sidecar. So you can see it in the diagram here. Your service mesh can run as a sidecar proxy alongside your application container. And sorry, that should say container within a pod. And one of the implications of this is that all your outgoing requests from your application will now go through your sidecar proxy. So let's see what happened because of this at shutdown. So chat, we use WebSockets for chat. To handle WebSockets gracefully, our shutdown is graceful. We give some grace period for the chat to end. Otherwise, it would be very disruptive for the end customer. Now, the service mesh, on the other hand, was shutting down as soon as it got a sick turn, which means any of the outgoing requests from the chat pods were just not reaching the rest of the system. And hence, one, the chats were not working for already connected WebSockets. And two, we were seeing connection refused errors. Now, in terms of the what we saw at startup, where the services were failing to start up and the SDKs were not loading, here the problem was the service mesh proxy was coming up a little bit later compared to the chat services. So the chat services were up first, and at startup, they try to retrieve config, they try to retrieve secrets. We use Vault, HashiCorp Vault to store our secrets, and we had to make a call out to Vault to retrieve the secrets. Now, if the sidecar proxy is not up, again, your outgoing request is not reaching Vault, you're not getting your secrets, and as a result, you're not going to start up. And that's exactly what we saw. So how do we fix this? At shutdown, it is simple. You have to add an annotation, and this is again the declarative nature. Add an annotation to the application pod to ensure that the grace period for the sidecar is the same. So you can see that the termination grace period for the application pod is 60. Similar for the service mesh, it says wait before you exit for 60 seconds. And when it came to remediation at startup, it's simple. You need to have a good retry logic for your configuration and secrets retrieval, and idempotent startup logic. It has to be repeatable. It cannot have side effects for running it multiple times. Unfortunately, as of the last release for Kubernetes, there is no good lifecycle management of sidecar containers. Again, this goes back to saying that Kubernetes understands the pod level and not really that much at the container level. So there is no story here yet, which means that they can operate pretty much independently of your application pod. However, there are talks about proper lifecycle management for the sidecars, and it's probably a matter of time before we have it. Once we have it, then because service mesh is a popular architecture for service mesh, I'm pretty sure we'll have it soon. And once we have it, we'll not have to worry so much about the management between different containers. So in conclusion, those were the lessons that we learned from running our chat services on Kubernetes, not just chat, other services also that interacted with our chat services. Kubernetes, as mentioned before, does abstract away a lot of details from you in terms of maintaining the number of instances you want to be running of a service, in terms of your configuration management, etc. However, there are caveats. We should almost always think about how our services behave in production. We should observe the resource usage patterns, make use of your metrics, think about how much memory your service is consuming, how much CPU it is consuming, and tweak accordingly. And it's not just about watching the pattern once you roll out the service, throughout the lifetime of the service, because they change as it does more or less. And then finally, striking a balance when configuring your QoS. Quality of service is good, but as we spoke about before, it's a question of balance because there is a cost factor as well. And lastly, building resiliency in your applications. Your application things can break, and your applications need to be resilient to it. So yeah, that is what I wanted to share about what we learned from running chat services in Kubernetes. Thank you.
Thank you so much, Priya. I thoroughly enjoyed your talk myself. And I was also trying to get to know Kubernetes myself. So thank you so much for sharing. At this time, anyone in the audience, big thank you to Priya, but most importantly, any questions at this time, feel free to post in the chat and we'll go ahead and get those questions answered for you guys. Anybody has any questions for Priya here on her talk, feel free to post them in the chat. We do have one question that just came in Question about graceful shutdown termination period matching the sidecar proxy. I believe that
What
question.
is
The
yeah,
question.
what is the question? Vijay works with me at ASAP.
Oh, yes.
Should I type asking what is the question? Oh,
So
yeah, I thought about that a little bit, Vijay, as I was thinking about this. It should be good enough. Uh, it should be good enough because there can obviously be some difference because they're not starting and stopping at the exact same time. But I feel like it should be good enough. Yeah, probably. Probably would make sense to make it greater.
does anybody else have any questions at this time? I guess I had a question myself as well. So I was seeing you could configuration manage the actual pods themselves, but when you're running into many containers in the same pod, does Kubernetes actually, is there a way to like pick up certain like CPU and MEMS per application as well?
Yeah.
Okay.
Yeah, so I think my demo, because I recorded it, I couldn't like really do it, but you can specify for each of your applications. So
Okay.
each of the container within the pod can have its own requests and limits for memory and CPU.
Okay, that makes sense. And I guess another question in my using of container management services with that connection refused, I oftentimes just assumed that there weren't enough CPUs and memory on the application, and then therefore it wasn't being registered in the service registry. Is that a fair assumption of events? Because I know you also gave a different use case and issues you were seeing with the sidecar proxy.
Yeah, so I hesitate to say that it could happen in the sense that it's not getting scheduled, so it's not getting registered, and then if you're trying to hit it, it can't discover it or something like that. But I I would think there would be many more reasons before it's related to the resources that would cause that kind of issue, if I were to guess.
Yeah, that makes sense. Thank you so much. Does
Yeah,
anybody
of
else have
course.
any other questions at this time? And if there are no other questions, let's all give a huge thank you to Priya for being here with us today. Thank you so much for sharing your knowledge about running applications in Kubernetes. And we hope everybody else has a good rest of their sessions. But thank you again for being here.
Thank you so much. This was a great thing to do on a Friday afternoon for me.
Absolutely, absolutely.
Thank you.
And of course, and everybody here in the audience, I'd encourage you to attend our next round of sessions. They will be kicked off in about 6 minutes. There are 5 other sessions going on. And also feel free to check out our networking tab. If you network with 3+ people, you can enter in to win a Women Who Code t-shirt. And just a heads up, we also have our expo running. There are a couple companies there hiring. If you're interested in your next opportunity, feel free to check out our expo. And finally, there will be a career coaching session, Navigating Your Career, happening in the VF Corporation booth. So feel free to check that out. Thank you again, Priya, and thank you
so
everyone
much.
in our audience for attending today.
Bye. Thank you.
Bye.